Then let's discuss the last one, the model fitting part. This is the most technically challenging one. And so, again, it interacts with the others. Usually you want to first explore. You could make predictions first and then fit, or if you once you have explored, you can fit your model, and then if your model fits the data well, you can use it to make predictions. So this whole, all these components usually interact, and you might not use all of them in a single project or paper, but usually when you address a system, you want to do a combination of those. And so, just worth thinking about it that in some sense, while these mathematical and simulation models have special features, in a bigger context, they're not necessarily unique, because you do this modeling in all of science. It's just you don't always use these explicit mathematical simulation models. Often, you have a conceptual model, you have assumptions about a system, and based on that, you come up with some hypotheses, or make predictions about what you would expect to see. And then you collect data, you're doing experiments, and then you compare what your model, your potentially conceptual model, produced and what the actual data showed you. This is, you can compare your hypotheses and predictions. The main difference here is now that instead of a sort of implicit conceptual model, we have an actual mathematical model. So we have to be in some sense more precise and say exactly what we expect to get out of it. And in our case, since these are mechanistic models, the models have specific mechanisms, and those we can explore and test. So the advantage of these mechanistic models versus a non-mechanistic is that in the non-mechanistic, you have your data, you look for patterns, you see if your null hypothesis or your alternative hypothesis is more in agreement with the data you find. But again, you can't say much about the mechanisms that gave rise to the data. You can say, okay, there's no link between this, let's call it now parameter, or this predictor variable, or this quantity we measured, and some outcome you're interested in. So you can see if there's a pattern or not, but nothing about the mechanisms. In these kind of models that we're using here, you directly test hypotheses or mechanisms because every model you formulate has mechanisms in it. So you can build, for instance, different models. Each model incorporates a different mechanism, a different hypothesis, and by comparing that to data, you can, get some support for some models and maybe reject other models that don't fit the data very well. So I'll walk through an example. It might be maybe the easiest to grasp that idea. So this is for a drug. In this case, it's for flu, neuraminidase inhibitors against flu. But this is very general, just an example. And the question here is, what is the mechanism of action of that drug? And we can postulate too, based on what we know about how the drug works. It could reduce virus production because the virus is stuck to the cell and can't come out, or it can reduce the rate at which cells become infected. So if those are our mechanisms or our hypotheses, we can build models for that. If we have the right kind of data, we can fit the models to the data and evaluate which model and therefore which mechanism is more supported by the data. So here is the model you've already seen. With the small addition, there's now this 1 minus f term, and that is basically the effect of the drug. And this is mechanism 1, where the drug reduces the rate at which cells become infected. So if you had a perfect drug, f would be 0, so that b times 1 minus f term would be 0. So there would be no more infection of uninfected cells. And for a not fully perfect drug, but very good drug, f would be maybe something like 0.9, or we don't know yet, but we'll let the model decide when we fit it to data. The second one is the hypothesis that virus production is reduced. And so here we multiply this, the virus production rate, P, by the term 1 minus E. And so again, if it's a the drug were perfectly blocking virus production, E would be 1, and this term would go to 0. So there would not be no more virus produced. So again, we can then fit it to the data and see which model would be better supported. And then for the better supporting model, if it fits the data well, if it can, you know, what the estimate for the parameter might be. There was supposed to be a figure here. I don't know where it went. Okay, well, we'll pretend there's a figure here. It should definitely be in the reading. Basically, what the figure shows you is the data, and the two models fit to the data. And based on the figure, you can already qualitatively see that one of the models works better. And you can also statistically do that. So in the DSARM package, you will see that we will look at AIC there, which is one criterion you can use to distinguish model fit quality. And it also suggests that one of the models is better, which is the model where the drug reduces production of infected cells. Sorry for that. I'll fix it on the slides when I upload it. I don't know where it went. So this way you can discriminate models. Oh, let me stop real quick. There's questions in the chat. Okay, Paul told me I said F should be 0 for a perfect drug. Though it's not true. F should be 1 for a perfect drug, and the same with E. And if it's a perfectly useless drug, then F and E would be 0. The question, what do you personally use as sufficient evidence to validate the mechanism of a specific model? That's tricky, and in my opinion, there is no hard criterion. So I like graphically. You know, if you have multiple models, you can compare them, and one model is better than the other. But if you have a set of bad models, your best model might still be a bad model. So it's worth, at the end, looking at it. It's, you know, you can do something like looking at residuals and see if there's a trend. However, for these kind of models, that's a bit trickier. I would basically just graphically evaluate and see if I think the model is close enough to the data, and that is kind of fuzzy. This is not a statistically, you know, p equals 0.05 things. But I think that's maybe as good as you can do, and I don't really trust people that use some statistical quantity and based on that say this model is good, this model is not good. In the end, we know the models are all not complete, they're just approximations, and maybe if we had further data, we would say, oh no, there's still things that the model cannot reproduce, so we need to further adjust it. So to me, that it's always sort of a, you know, given that data, this model seems to explain the data pretty well. So maybe that answer is more vague than you would hope for, but to me, that's sort of the most honest way of going about it. Just saying, okay, this looks reasonable in this case. There's another question somewhat related. When you compare models that represent different mechanisms, the models compared will vary in their complexity. So meaning they have more parameters or they have a different structure. And will that cause problems? If you use things like AIC or other measures, they can deal with that. They don't need models that are nested, so they can you know, compare models even if they're structurally different. Or if you have enough data, you could use approaches like cross-validation and then evaluate the model on the holdout data. And again, these approaches work even if the models are not sort of one model is within the other model, but structurally different. So that is usually not causing much of a problem. Keep typing the questions in the chat box. As I glance over there, I'll answer them. Okay, resuming here. So you can use models if you build multiple models to differentiate mechanisms. So you could say, well, we built 3 models that each incorporate a different mechanism. We fit them all to the data, and based on that, model 1, you know, has the mechanism in it that seems to be most closest to the data. As you do that, you always, you know, estimate parameters in your model. Depending on how much data you have, you can estimate all of the parameters in your model. Often that's not the case. You might have to keep some fixed based on prior biological knowledge, because you might not have enough data to get good estimates for all of them. But you might definitely want to estimate the parameters of interest. So in this case, we could estimate the efficacy of the drug. So in this example, if with the best fit estimate of the model we think is the best model, once we decided it's not just the best model, it's also a good enough model that we can maybe trust the parameter estimates, we get some value out. So let's say we get E equals 0.98. That suggests that that drug would reduce virus production by 98%. So that the nice thing with these models here is that the parameters have biological meaning. So if you fit some kind of regression model or some more complicated statistical models, often the parameters themselves don't have a direct biological meaning. They might tell you how important that variable is that is associated with that parameter, but otherwise they don't give too much insight. Well, here they are usually biologically meaningful parameters. For instance, DI is the death rate of the infected cells, so the inverse is the lifespan of an infected cell. That's something we might want to know just by itself. So you always get these parameter estimates when you fit. You can even estimate parameters with just a single model if you don't want to do model comparison. So if you have a model that you already know, this is a pretty good model, I don't need to compare it with other models, all I want to do is estimate the values of certain biological parameters. You can fit that model to the data and get best fit estimates out. So that's something you will always get. When you fit only a single model, you can do a little bit of mechanism testing. So something similar to null hypothesis testing. In this case, you could test if the drug has an effect. That would mean E is greater than 0, or doesn't have an effect. That would be E approximately 0. Though I think it would actually be better if you formulate a model that has the drug in it. So E, and you let E fit, and then you have another model where you just take that out and fit this and see how it compares. And then if you have more complex hypothesis mechanisms, you do need distinct models. So if you have, the thought that there might be multiple competing hypotheses, I would start with multiple models, fit them to the data, and then take the model that works best, and then maybe look at the parameters and see what they mean. In either case, even if you're not really interested in the parameter values, you should look at them anyway, because that's another sanity check. So, if you have a model that fits the data well, but the prediction is that infected cells produce 1 trillion virus particles per second, that's not right. There's no virus that is being produced at such a high rate. Or if it predicts that the infected cells live for 1,000 years, that's not right either. So then, something isn't quite right with the model. And again, because these parameters have biological meaning, you can look at them and you can do sanity checks and say, okay, do they make sense or do they not make sense? And if they don't, you might have to adjust your model. The question is, can you estimate more than one parameter at once? Yes, you can. So in principle, you can estimate every parameter in your model, including the initial conditions, which for purposes of model fitting are treated as parameters that can be estimated. The practical limitations is that often your data is not rich enough. Usually if you have, let's say, uninfected cells, infected cells, virus, you might only have data on the virus and not the other ones. And so if you only have data on some of the components of the model, it might not be enough to allow you robust estimates for all the parameters. When you're trying to do that, you might get sets of parameter estimates that basically give you almost the same quality fit, if you look at it in some statistical sense, but completely different values. And so that's an indication that you're trying to overfit. Your model is too complex for the data you have. And then in that case, you might have to fix some of the parameters in the model based on outside biological knowledge. For instance, if you know that these infected cells only live for 12 hours and there's good evidence from other experiments, you can fix that value and therefore reduce the number of parameters you fit. But in principle, there's nothing preventing you from fitting as many parameters as your model has. So another question, if model comparison result depend on what parameter values are used. But parameter estimate, it depends on model structure. How do you recommend dealing with that? Well, if you have different models with different mechanisms, then the components that influence these or are parts of these mechanisms you want to let fit or be variable and fit. So basically, you let the computer decide what the best possible value is for this one. So you can then fit these different ones and you let the computer decide, okay, this is the best I can do with this kind of model. And then you do it for the other one and it says, okay, this is the best I can do with that other kind of model. And so in that sense, the model comparison doesn't depend on the parameter values because you let the computer try all the parameter values and say, okay, this is the best I can do with this model. And basically then you pick a model and then you have the best model and the values that go with it. You don't have to do it again then because your best fit for that model already has the estimates in it. So in that sense, there isn't really a conflict and you don't have to go back and forth because you do want to fit those models, those parameters that go with the specific mechanism. There's a question, if you assess multiple parameters, do you assess their correlation? Yes, but not in the sense you would do it with the regression model where you have different predictors and you have data on those predictors. This is actually not the case here, right? We don't have data on those parameters. But it could be, for instance, in this virus infection model, you can have the a virus that is really good at cranking out new virus particles once they're inside a cell, but it's not very good at infecting cells. Another virus strain could be very good at infecting cells, but then these infected cells don't produce a lot of virus. Those two types of viruses could lead to an overall similar viral load. So in that sense, while I wouldn't call it correlation, you have the problem of identifiability, that different combinations of parameters could give you almost the same pattern. And if the only pattern, the only data you have is total virus load, you might not be able to distinguish between those. So that comes back to what I said earlier, you might be overfitting. You might, in this instance, not be able to fit both the parameter B and the parameter P, which is the infection rate and the production rate, but you might have to actually fix one of them. The way you test that best, and that's it's in one of the DSIRM apps, you're asked to do that, is you take your model, you set parameters, you simulate data, then you put a little bit of noise on it, and then you pretend this is the real data. You run your fits, and then what you would need to find is that your best fit estimates are what you stuck in to produce the artificial data in the first place. If you can't recover that, it means you're probably overfitting and you have some kind of identifiability problems in your system and you will have to adjust. And in this case, adjusting means making the model simpler. Or if you can get more data, but that's of course the harder part. Often you just have the data you have. And so then you might have to simplify the model. I sort of touched on those. So in some sense, conceptually, fitting these mechanistic models and fitting regression models are very similar, but they still tend to be technically more challenging. Well, what I mean by conceptually the same is a lot of the machinery applies. So, if you know how to fit a regression model by minimizing the sum of square residuals, you can do exactly the same here. If you're familiar with some kind of Bayesian fitting approach, you can do exactly the same here. If you use some kind of likelihood approach, you can do the same here. So in that sense, all of that machinery carries over. And that's why, coming back to the first lesson, why I don't like to call the phenomenological models statistical models, because we can use these mechanistic models very much in a statistical way as well. It is technically still harder because these models often have these issues where certain parameters can make up for others, and then when you're trying to fit it, your numerical routine might have a hard time finding the best fits, and you might get stuck somewhere, and you might have to try different values. And so just the technical details tend to be more challenging of fitting those kind of models. But conceptually, for them, most of what you do with regression models applies. Of course, another thing you do want to keep in mind here is that this data is almost always time series. So anything that applies to time series data, which means what's happening at time 10 likely depends on what happened at time 9 and 8, might need to be taken into account as well. So often we assume that the data is not correlated and then fit it in that form. The good thing is with these mechanistic models, I think you've learned sort of more, especially when the model fails. If you fit a regression model and you don't get a good fit, well, it means you have to keep building better models, right? You might have to include an interaction term, or you might have to include a square term, or you might have to move to some more complex model that goes beyond linearity or something like that. But you don't necessarily learn something. You just learned that the simpler model didn't work. You have to take into account some more aspects. Here, if you build a mechanistic model based on what you think is going on about the system and it doesn't fit the data well, you've learned something. You realize, no, I thought whatever interferon was doing the following thing, but it just doesn't seem to fit the data. So I learned that this process is wrong or not sufficient, or I'm missing something. And so this, you can then build iteratively your knowledge of the system. So in that way, I think it's actually quite insightful when these mechanistic models fail. Of course, if you build a stupid model in the first place and it doesn't work, then you didn't learn much. But assuming you built the model based on what you think is going on in the system and it doesn't work, you've learned something. And I think it's useful reporting. I like reading papers that said, okay, we tried this model, we thought it could work, but it didn't. Now, to publish something, usually in the end, you have to have a model that works. So you need to keep building until you get one that looks reasonable enough. But I find it useful to read the other components as well. I already said those things. So always check your model. If you get in the weeds of doing stats and all that, sometimes people forget to step back and do a reality check, right? So if you have very complex models and you have one that statistically is really good, you might stop there. That's not a good idea. You always have to step back and say, okay, is this model any good? It might be the best, but it might still be bad. And then we already addressed the issue about complex models being more tricky to fit because they might give you fits, but for spurious reasons, because there are a lot of processes that might lead to the same outcomes. So therefore, it's always important to check your parameter estimates to make sure they make biological sense, make sure you're not overfitting, and keep the model simple. And so this quote along those lines has been attributed to John von Neumann, said that 4 parameters, he can fit an elephant, and with 5 can make wiggle his trunk. And of course, someone tried that. So if you go to that link, you'll find 4-parameter equation that is the elephant, and parameter number 5 makes the trunk wiggle. So yeah, if you want to give it a try. There's several apps in DSIRM. There's the influenza drug model, which shows you an example of fitting, but doesn't actually talk much about fitting. And then the ones in the model fitting section dig a little bit deeper. Again, this is the technically most challenging topic. I also understand that quite often it's the most interesting one, so that's a little bit of attention to try to cover this topic that is definitely of interest, but is also the hardest in especially a course as short as this one. So given the nature of this course that it's so short, we can only give you sort of pointers here and hope you get started. And then it's really a lot of experience by doing this and fitting these models. So I'm just going to kind of close again with that overview slide. Usually you would want to start with exploration, and then you can, if you trust your model, move on to prediction. And those you can do what I call data free. That of course doesn't mean free of realism, but you don't need any data to fit to. So you can build the model based on what you think is going on in the system, take parameter values from the literature, and then run your model without having to fit it to data. If you have data, you can do the additional thing of statistically, rigorously comparing hypotheses, testing mechanisms, and getting values for parameters that are estimated. And as I mentioned before, often a project might use different approaches. So, pretty much always you do exploration, even if your goal in the end is fitting or prediction. Just while you build your model, you need to explore it to make sure it works, things behave the way you think it should. Sometimes you stop at the exploration and that's the whole project. Sometimes you might move on to the main part where you say, okay, my main goal is actually fitting, and then you might fit multiple models. And depending on, you know, how much you trust the models, either with fitting or without fitting, you can use them to make predictions.